Welcome to The Explainer. Today, we're taking a high-energy journey straight into the absolute core of back-end engineering, databases. We're going to demystify exactly how your data survives the harsh reality of an application closing down. If you've ever wondered how your to-do list doesn't just, vanish into thin air when you swipe away an app, you're in the exact right place.
Okay, let's dive into this structural roadmap. First up is the persistence problem, followed by choosing the right database, migrations and data types, table relationships explained, queries and security, and finally, indexes and triggers. We're moving logically from basic hardware problems all the way to advanced optimization.
Section 1. The persistence problem. Keeping data alive.
So, before writing a single API, every backend engineer has to solve this fundamental problem of keeping data alive across sessions. Think about a simple to-do list app. If you check a box and close the app, that checkmark better be there tomorrow, right? That survival of data is what we call persistence, which brings us to a really foundational question. Why do we need databases in the first place? If we just want to save simple data, why use heavy, complex software systems? Well, to understand the software, we actually have to look at the hardware.
On the left, we've got primary memory, or RAM. Now, RAM is incredibly fast, but it's expensive, severely limited in capacity, and crucially, it's volatile. You turn the power off and bam, everything in RAM is wiped out completely. On the right, we have secondary storage, your hard drives or SSDs. Disk storage is relatively slower, for sure, but it's cheap, it's abundant, and most importantly, it is persistent. Databases exist specifically to manage that massive, persistent disk storage efficiently.
But you might be wondering, why not just use a simple, basic text file on that hard drive? Welcome to what I like to call the text file trap. First off, your parsing speeds are disastrous. Your application code has to painfully split lines and search character by character. Second, there's zero structural enforcement. You could accidentally save a word where a number should absolutely be. But the real killer here? Concurrency collisions. Imagine two users trying to modify a text file that lists an account balance of $40 at the exact same millisecond. One adds 20, the other subtracts 20. Who wins? A text file has zero mechanisms to resolve this, leaving your data completely corrupted.
Section 2. Choosing the right database, relational versus NoSQL. Because of those severe text file limitations we just talked about, the industry evolved toward database management systems. This is a massive architectural choice for developers, and we essentially have two distinct paths. On the left, we have relational databases, like Postgres. These are rigid. They organize data into strict tables and rows, forcing you to define a structure before you insert literally anything. This is absolutely perfect for structured systems, like a CRM. On the right, we have non-relational or document databases like MongoDB. These are highly flexible. You can just dump completely unpredictable data structures into them on the fly, making them great for a CMS, where a blog post might randomly include a video, an image, or just raw text.
So which do we choose? And this brilliantly illustrates why Postgres is the industry darling. It's totally free, it's open source, and it sticks really tightly to the SQL standard. But the absolute clincher is its unmatched JSON and JSONB support. This means Postgres actually gives you the flexible, dynamic NoSQL superpowers of a document database right inside a strictly enforced, highly secure relational system. It's literally the best of both worlds.
Section 3. Migrations and data types. Architecture building. Now that we've chosen our database engine, how do we actually define and alter our database schema over time without completely breaking our live production systems? The answer is migrations. These are version-controlled SQL scripts. In a professional back-end environment, you never just open a graphical interface, click a button, and randomly add a column to a table. No way. Instead, you write actual code, predictable, sequential files that track the evolving state of your database over its entire lifespan.
Let's look at how this builds into a safe workflow. Notice the migration lifecycle here. Step 1 is the up migration. This is where you execute SQL to apply changes to your architecture, like creating a brand new users table. But step 2 is equally critical, the down migration. This is a script specifically written to revert those exact changes. If you deploy an up migration and your production app suddenly crashes, that down migration acts as a crucial rollback safety net, allowing you to instantly revert the database back to a healthy state.
When creating these scripts, choosing the right data type is crucial. And I want to debunk a major industry myth right now. You'll constantly see developers using varchar 255 to store strings. But honestly, that 255 limit is just a random relic from older MySQL conventions.
In Postgres, there's essentially zero performance benefit to using it. The official recommendation is to simply use the text data type, which has no arbitrary limit. You then enforce length restrictions smoothly on your application level, keeping your migration so much cleaner.
Section 4. Table Relationships Explained. Connecting your data.
Defining tables is really just step one, because a single table is simply never enough for a complex backend system like a project management tool. The real magic happens in how your data connects. We have three main mapping strategies. First, a one-to-one relationship, like linking a single user to a single profile using a shared key. Next is one-to-many. Think of one single project containing many tasks. You implement this by placing a foreign key on the task row that points directly back to the project ID. Finally, many-to-many. A user can be in many projects, and a project can hold many users. To map this, we create a dedicated linking table right in the middle, utilizing a composite primary key, combining both IDs to lock in that specific relationship.
Now, what happens when you delete connected data? Well, that's governed by referential integrity. These are strict database rules ensuring your relationships remain valid so you don't end up with broken, orphaned data. For instance, if you try to delete a user who owns several tasks, the database steps in. Depending on your rules, it might restrict the action, completely blocking you from deleting the user. Or it might cascade, which automatically deletes every single task associated with that user to keep your database perfectly clean.
Section 5. Queries and Security. Safe data interaction.
Okay, we've structured our database beautifully. Now we need to shift focus to how our back-end application actually interacts with it, and our absolute top priority is safety. Enter the ultimate shield, parameterized queries. These are essentially empty placeholders, or slots, inside your SQL code. When a user types something into a search bar on your front end, you never ever inject that raw text directly into your SQL command. Instead, you securely fill that empty slot at runtime.
So why does this matter so much? To defeat SQL injection. Without parameters, a malicious attacker could type a command like delete all users into a simple web form, and your database might actually execute it, literally destroying your business in a millisecond. But by using parameterized queries, the database treats that destructive input purely as a harmless, literal text string. It simply searches for a user whose literal name is delete all users, finds nothing, and your database remains completely secure.
Section 6. Indexes and Triggers. Advanced Optimization.
Once your application hits enterprise scale, mere correctness just isn't enough. We need immense speed and deep automation. This brings us to a critical performance problem. How do we avoid scanning a million rows? See, if you ask a database to find a specific task, its default brute force method is a sequential scan. It literally starts at the very beginning of your hard drive and checks every single row one by one until it finds a match. On a massive, production-scale database, that is disastrously, unacceptably slow.
Now, what's really interesting about this slide is how it solves the problem using a simple book analogy. Think of a standard book index. If you want to find a specific topic in a massive textbook, you don't read page by page, right? You flip to the index at the back, find your topic, and jump straight to the exact page number. A database index functions identically. It's a dedicated, highly ordered lookup table that maps a key, like an email address, directly to its precise physical location on the hard disk, granting you practically instant data retrieval. But what about automation? That's where database triggers come into play. These are custom functions that automatically execute in response to specific events happening inside your tables. Imagine writing application code to manually update an updated@ timestamp every single time a user alters their profile. It's tedious and it's error-prone. Instead, you write a database trigger. The exact millisecond a row changes, the trigger fires automatically behind the scenes, flawlessly stamping the new time right at the database level.
And there you have it. We've taken raw hardware, solved the persistence problem with elegant relational architecture, locked it down with strict parameter security, and supercharged the performance with enterprise-level indexing. Your database is now structured, secured, and indexed. So what does this all mean? The only question left is, what are you going to build with it? Are you ready to architect something that survives the ultimate test of scale? Take these concepts into your next build. Thanks for joining this incredibly deep dive on the Explainer.